There is something about the hour before sleep that makes the world feel less certain than it did at noon. The chair you're sitting in, or the bed you've already found, it holds you, and you don't question it. And that not questioning is so automatic that the whole architecture of trust goes unexamined. The floor holds the chair, the ground holds the floor. And somewhere beneath all of that, if you keep pressing downward through soil and mantle and the slow churn of the deep earth, you eventually arrive at matter itself, the raw stuff, protons, neutrons, the locked humming arrangement that everything physical has agreed to hold. And here is where it gets strange, not frightening, not yet, just strange, because physics, which has spent several centuries being very good at describing matter, has not been able to confirm that the arrangement we call ordinary is the lowest one possible. There may be a ground beneath the ground. The wool blanket, if you have one, has a particular weight tonight. That weight is atomic. Every vour, every thread, every gram of pressure settling across your legs is made of the same basic ingredient. Nuclei ringed by electrons, held in patterns that chemistry understands and biology uses, and physics, quietly, has never fully resolved. It isn't that the atoms are wrong, it's that wrong might not be the right word. The better word, the word that physicists use when they're being careful, is metastable. Metastable means stable enough. Stable for now. Stable in the sense that nothing has disturbed it, not that nothing could. An egg balanced on a countertop is metastable. It isn't falling. The forces on it are, at this moment, in balance. But it is not in its lowest energy state. The floor is its lowest energy state. And the only thing standing between the egg and the floor is the absence of a nudge. That's metastable. That's the word. And the unsettling thing, the thing I keep returning to, the thing I haven't quite made peace with, is that some physicists believe ordinary matter, the matter in your blanket and your bones and the walls of whatever room you're in right now, may be sitting on that countertop, not falling, not about to fall, but not in some strict dynamic sense, at the bottom. This idea didn't arrive loudly. It wasn't announced at a press conference or printed on the cover of a magazine. It came in the form of a hypothesis, a careful, hedged, technically dense hypothesis, published in 1984 that asked a question so unsettling most of the field initially chose not to dwell on it. What if strange quark matter, a form of matter built from 3 types of quarks rather than the 2 that protons and neutrons use, is actually more stable than everything we observe? What if ordinary matter is the egg? The 3 types of quarks are called up, down, and strange. Protons contain 2 up quarks and 1 down quark. Neutrons contain 1 up and 2 down. Strange quarks don't appear in ordinary matter at all. They're heavier, they're unstable in isolation, and they decay quickly into the lighter varieties under normal conditions. Everything you have ever touched is made entirely without them, which makes the hypothesis even harder to sit with, because the argument, and it is a real argument, not a fringe one, a real piece of theoretical physics that has never been disproven, is that matter built from all 3 quark flavors in roughly equal proportions might sit at a lower energy level than the 2 flavor matter we're made of. Not by a dramatic margin. The difference, if it exists, would be modest in absolute terms. But energy states don't care about margins. A state is either lower or it isn't. And if strange matter's energy per particle is lower than ordinary matter's energy per particle, then ordinary matter is, by definition, not at the bottom. It is waiting, in some technical sense, for a reason to change. The reason it hasn't changed, the reason you exist, the reason the room around you still has its shape, is a barrier. A very high, very stubborn energy barrier that sits between ordinary matter and the hypothetical lower state. To convert a proton into something stranger, you can't just rearrange a few quarks. The weak nuclear force has to intervene. Strange quarks have to be produced. Multiple quarks have to change flavors almost simultaneously, which is, there's no softer way to say this, extraordinarily unlikely to happen spontaneously. The barrier isn't thin. The lifetime of a proton waiting to fall, if it's waiting at all, would be incomprehensibly longer than the current age of the universe. So we are not in immediate danger. But safe and at the bottom are different things. And somewhere in the back of physics, not in the headlines, not in the public conversation about matter, but in the steady, careful literature of theoretical work that accumulates in journals and conference proceedings and the margins of graduate students' notebooks, this question has been sitting unresolved for over 40 years. There may be a substance the universe prefers over everything we know. A state of matter so perfectly stable that it makes iron look fragile and atoms look like scaffolding. Something that reached the true bottom, while ordinary matter stalled on a ledge above it, held in place by a barrier that, under the right conditions, under the right encounter, might not hold. That substance has a name, and the night is still early enough to go looking for it. Quarks are not things you can hold. They are not small enough to be small in any way that helps. They exist below the threshold where size stops being a useful concept, where the very act of trying to locate something changes what you find. And yet they are real. They have mass, they have charge, they interact. The proton in your blood right now contains 3 of them, 2 up quarks and 1 down quark, bound together by a force so powerful it has no weakening with distance. The more you pull quarks apart, the harder the force pulls back, which is why isolated quarks essentially don't exist in nature. They come in groups. Always. Up quarks carry a charge of positive 2/3, down quarks carry negative 1/3. Combine 2 ups and a down and the charges sum to exactly positive 1. A proton. Combine 1 up and 2 downs and you get 0. A neutron. This arithmetic is almost insultingly tidy. The universe built everything we have ever seen. Every element, every molecule, every grain of sand and strand of hair and distant star. From these 2 ingredients, shuffled into triplets, held together by a force with no off switch. That's the ordinary version. There is a 3rd quark, heavier than both the up and the down. It carries the same charge as the down quark, negative 1/3, but it has something the others don't, a quantum property that physicists, with unusual whimsy, name strangeness. The strange quark is not exotic in the sense of being rare in the universe's accounting. It was abundant in the very early universe, produced freely in the heat of the first fractions of a second. But it is unstable in isolation. Left alone at low energies, a strange quark decays via the weak nuclear force into an up quark in about 10 to the power of -8 seconds, taking its strangeness with it. This is why ordinary matter, the matter that survived, the matter that cooled and condensed and eventually became you, is essentially strangeness-free. The strange quarks didn't survive the early universe's cooling, they decayed. What was left was the 2-flavor world, and for a long time that felt complete. 2 flavors, protons, neutrons, everything built from them, done, except, and this is the part I keep getting stuck on actually, the part that resists being filed away neatly. The physics of how quarks share energy suggests that 2-flavor matter might not be the most efficient configuration. It might just be the most available one. Here's the machinery underneath that. Quarks are fermions. Fermions obey the Pauli exclusion principle, which means no 2 identical fermions can occupy the same quantum state simultaneously. If you want to pack quarks into a small space, and inside a proton, you're packing them into a very small space. The quarks with the same flavor start crowding each other out. The lower energy states fill up. New quarks, if they arrive have to climb into higher energy levels. This crowding, this forced elevation, raises the overall energy of the system. It is not dramatic, you wouldn't feel it, but it is real, and it is the reason matter's energy budget is slightly higher than it might otherwise need to be. Now add a third flavour. A strange quark has a different quantum identity than an up or down quark. It doesn't compete for the same states. When strange quarks are present alongside up and down quarks in roughly equal proportions, the crowd spreads across 3 sets of energy levels instead of 2. The lower states refill not because anything was added, but because the available space expanded. The quarks settle lower. The total energy per particle drops. It's like, okay, this is the moment a metaphor either helps or embarrasses itself, so I'll use it carefully. It's like being in a room with 2 chairs and 3 people versus a room with 3 chairs and 3 people. The same number of people, the same people, just one more place to sit, and the whole room relaxes. The energy per baryon, the energy carried by each unit of nuclear matter, is theoretically lower in strange quark matter than in ordinary matter. Lower than in a proton, lower than in a neutron, lower, if the hypothesis holds, than in iron 56, which was supposed to be the most stable nucleus in existence, the endpoint of stellar fusion, the bottom of the ordinary periodic table. Strange matter, if it can form and persist, sits below all of that. The catch, there's always a catch, is that the strange quark is heavier than the up and down quarks. Adding strange quarks to a system costs energy up front because you're producing heavier particles. The question is whether the energy saved by spreading across 3 flavor states outweighs the energy spent generating the strange quarks in the first place. And the frustrating answer, the answer that has kept this hypothesis unresolved for 4 decades, is that it depends. It depends on the values of parameters, the bag constant, the strong coupling constant, the strange quark mass, that we know approximately but not precisely enough to settle the question from first principles. The calculation can go either way. Some parameter ranges make strange matter stale, others don't. The universe knows which it is. We don't yet. What we do know is this: the logic is clean, the mechanism is real, the Pauli principle applies, the energy levels exist, the third flavor genuinely does provide more room. Whether that room is enough to bring strange matter below ordinary matter is the unsettled part. But the direction of the effect is not in dispute. 3 flavors, all else being equal, means lower energy. The universe, in every other context we know, eventually finds its lowest energy state. It has 14 billion years of patience. Ordinary matter has been sitting in a 2-flavor arrangement for all of that time, comfortable, stable-ish, doing everything matter does, forming stars, building planets, assembling the molecules that eventually learn to breathe and wonder and lie awake at night. But the strange quark exists. It was always there, heavier, unstable in isolation, decaying fast under ordinary conditions, and under the right conditions, under pressure so severe it makes the word pressure feel inadequate, in environments where the barrier between ordinary matter and something lower can actually be crossed, the strange quark might not decay. It might join. It might become part of something that the up and down quarks on their own could never quite reach. What those conditions look like, and where in the universe they might already exist, is a different question. One that starts not in a laboratory and not in a textbook, but in a very particular kind of silence. Arnold Bodmer published his paper in 1971 in Physical Review D. It was not rejected. It was not controversial. It did not generate letters of outrage or lengthy rebuttals, or the particular academic drama that sometimes follows a genuinely threatening idea. It was received, filed, cited occasionally by a small number of people working in adjacent areas, and then, not forgotten exactly, but not remembered either. It sat in the literature the way certain papers do, present, technically available, waiting. The paper was called Collapsed Nuclei. The argument inside it was careful and specific. Bodmer was asking whether nuclear matter, compressed beyond the density of an ordinary nucleus, might reach a state of lower energy than anything in the standard picture. Not neutron star matter, not the interior of a collapsing star, but something more fundamental, a rearrangement of the quark content of matter itself into a configuration that physics had not yet seriously considered. He was working before the quark model was fully established, which makes the paper more impressive and also harder to read, because the language he used was not quite the language the field would later develop to describe what he was pointing at. He was right before the vocabulary existed to say so clearly. That's a particular kind of loneliness in science. Not the dramatic loneliness of being ridiculed. That at least implies an audience. This was quieter. Bodmer's paper arrived in a field that was still assembling the conceptual tools it would need to understand what he'd found. The quark model was young. Quantum chromodynamics, the full theory of the strong force, was being worked out across the 1970s in pieces, in arguments, in a string of papers that slowly locked the formalism into place. By the time the field had the language, Bodmer's paper was already old enough to be background. He named the thing he was describing collapsed nuclei. The name didn't stick. The idea did eventually, but under a different name, attached to a different paper, written 13 years later. There's something almost stubborn about that, the idea surviving the name. In 1984, Edward Witten, working at Princeton, already one of the most prominent theoretical physicists alive, arrived at essentially the same place Bodmer had arrived, through a different path, with different tools, and with the full machinery of QCD available to make the argument more precisely. His paper was called Cosmic Separation of Phases. The argument was sharper, the language was current, and because it was Witten, the field paid attention immediately. The hypothesis acquired a name, the Bodmer-Witten Conjecture eventually once people went back and found the earlier work, and a research program and a literature, and a set of open questions that physicists are still working through today. Witten has said in various contexts that he was not aware of Bodmer's paper when he wrote his, that's not damning exactly. Papers get missed. The literature is large, and 1971 is far enough back that the indexing systems and citation networks we rely on now were not quite what they are today. But there's something worth sitting with in that gap. 13 years, the same idea, different receptions. What Bodmer noticed specifically was that when you push nuclear matter hard enough, when you force quarks close enough together, that strange quark mass stops being the dominant consideration. When the energy savings from the three-flavor configuration start to outweigh the energy cost of producing strange quarks, the system can, under some parameter ranges, settle into a state with lower energy per baryon than ordinary nuclear matter, lower than iron, lower than anything on the periodic table. He expressed this carefully. He did not claim it was true, he claimed it was possible. He worked through the conditions under which it would be true, and he identified the parameters that the answer depended on, and he left the question open because the data at the time could not close it. That's what the paper was. A careful door left open. Nobody walked through it for over a decade. This happens in physics more than the public narrative of science tends to acknowledge. The history as it gets retold, the breakthrough, the moment of insight, the paper that changed everything, tends to compress time and assign credit cleanly. But the actual texture of how ideas move through a field is messier and slower and often less fair than the compressed version. Some ideas arrive before their infrastructure. Some papers are correct and dormant simultaneously, waiting not for someone to prove them wrong but for someone to prove them right, or even just to notice them at the right moment. Bodmer's paper was not wrong in 1971. It was early, which is a different condition entirely and not a comfortable one. The strange matter hypothesis, the full version, the one with the name and the research program and the 40 years of follow-up, is usually dated to 1984. Witten's paper, that's the timestamp the field uses, and it's accurate in the sense that the hypothesis as the live scientific question began there, gained traction there, generated the conversations that are still ongoing, but the ground beneath it was laid somewhere quieter. In a paper that was technically present and functionally absent for 13 years, by a physicist who was right before anyone was quite ready to hear it. Whether that matters to the physics is a fair question. The physics doesn't care about credit or timing. The universe was not waiting for either Bodmer or Witten before deciding whether strange matter was stable. The answer exists independently of who found it first or when, or whether the finding was noticed. But it matters to something else, to the shape of how knowledge actually moves, to the reminder that being right and being heard are separate events, sometimes separated by a long time, sometimes not bridged at all. Bodmer's door is still open. Nobody has walked through it definitively, not yet. There is a specific kind of paper that changes not what a field knows, but what it allows itself to ask. The finding isn't a proof, the equations don't close into certainty. The conclusion read carefully is something closer to, here is a door, here are the reasons it might open, here are the conditions under which opening it would not contradict anything we currently understand. This kind of paper usually arrives and is received politely and moves into the literature without much velocity. Usually. Edward Witten's 1984 paper was not usual. Not because the argument was more decisive than other conjectures, it wasn't quite, but because of who was making it, and because of what the field did with the permission that implied. Witten was, by 1984, already the kind of physicist whose papers get read the week they appear. String theory, supersymmetry, topological field theory, he had left marks across theoretical physics that most physicists spend entire careers trying to approach. When someone with that kind of earned credibility publishes a speculative paper, the speculation carries a different weight than it would from an unknown. Not because credibility makes a conjecture more likely to be true, it doesn't, the physics doesn't care, but because it lowers the social cost of taking the idea seriously. Other physicists can follow the thread without it looking like a detour from serious work. The conjecture becomes, in some informal but real sense, licensed. That's what Witten did with strange matter. He licensed it. The paper itself, Cosmic Separation of Phases, was not purely about strange matter stability. It was about the QCD phase transition in the early universe, about how quarks and gluons might have separated into distinct regions as the universe cooled, and about the remnants that such a transition might have left behind. Strange matter stability was, in that paper, more of a thread than a centerpiece, but the thread was the part that pulled, the part that got cited, the part that spawned the research program that is still running. The core of the argument was this. Ordinary nuclear matter, protons, neutrons, the two-flavor quark matter inside them, is what we observe. It is stable by every measurement we have, but stable in physics has a technical meaning that is more careful than the everyday one. A system is stable if it is at a local energy minimum, if small perturbations return it to the same state rather than pushing it into something else. Ordinary matter passes that test easily, but local minimum is not the same as global minimum. There can be a lower valley somewhere else in the energy landscape, one that ordinary matter never falls into because the barrier between them is too high to cross spontaneously. Witten's conjecture was that strange quark matter, matter built from up, down and strange quarks in roughly equal proportions, deconfined, free of the nucleon structure that organizes ordinary matter, might be that lower valley, might sit at a lower energy per baryon than iron, than neutrons, than anything the periodic table contains, might be, in the technical language, the true ground state of strongly interacting matter. Might. That word is doing a lot of work, and Witten did not hide it. The argument depended on the MIT bag model, which was the best available tool for describing quark matter at the time. The bag model imagines quarks as existing inside a bubble, a bag, where the strong force permits their relative freedom, surrounded by a vacuum that exerts an inward pressure described by a constant called the bag constant, whose value was not precisely known. The stability of strange matter within this framework turned on that constant. For some values, strange matter came out stable. For others, it didn't. The calculation was honest about this dependence. Witten was not claiming to have measured the bag constant precisely enough to settle the question. He was claiming that the range of values consistent with other known physics included values for which strange matter would be absolutely stable, and that this possibility deserved serious attention. The paper included, and this is the part that sent tremors through the field, the part that made the conjecture feel heavier than a typical speculation, a follow-on observation about what absolute stability would mean. If strange quark matter is the true ground state of hadronic matter, then in principle ordinary matter is metastable. Not unstable in any practical sense, not about to decay, not dangerous under normal conditions, but sitting above the true bottom. And if a seed of strange matter were introduced to ordinary matter under the right conditions, the energetics would favour conversion. The ordinary matter would have somewhere lower to go. Whether it could get there, and how fast and under what circumstances, these were separate questions, hard questions, questions with answers that depended on physics that the 1984 paper did not pretend to fully resolve, but the logical structure was clean. Ground state means everything else is above it. Above means, thermodynamically, that the direction of change is downward. The paper was careful not to say this was likely or imminent or dangerous, but it said it was possible, and it said it coherently, and it said it in a way that other physicists could engage with rather than dismiss. Fahy and Jaffe published a detailed follow-up the same year, actually the same journal issue, which must have made for an unusual read, working through the parameter space of the bag model more carefully and mapping the regions where strange matter stability held. They found the window was real, narrow perhaps, dependent on values of the strong coupling constant and the strange quark mass that were only approximately known, but genuinely present in the parameter space. Not ruled out. The phrase they used, and that gets cited often, is that stability of strange matter at zero pressure is unlikely but possible. Unlikely but possible. That phrase has had a strange career in the literature. It is honest. It is technically defensible. It is also the kind of phrase that means different things to different readers. To the person looking for permission to worry, it sounds like a warning. To the person looking for reassurance, it sounds like a dismissal. The phrase itself doesn't change, the reader does. What Witten's conjecture changed permanently was the set of questions the field was allowed to take seriously. Before 1984, strange matter stability was not a topic with a research program. After, it was. Papers on strange stars, on strangelets in cosmic rays, on the safety implications for particle accelerators, on the possibility that dark matter is ancient quark nuggets from the early universe, all of it traces back, directly or indirectly, to that 1984 paper. Not because Witten proved anything, because he asked, carefully and publicly and with the full weight of his reputation behind the asking whether the universe might prefer something other than what we're made of. The door he described is still standing. It has not been opened. It has not been sealed. Physicists have spent 4 decades examining the frame, measuring the gap beneath it, pressing an ear to the wood. What they found is that the door is real, the hinges are not rusted, and whether it's locked depends on numbers the universe knows, and we are still working to learn. That's where the hypothesis lives. Not in proof, not in refutation. In the specific patient uncertainty of a conjecture that was responsible enough to name its own conditions and honest enough to admit it couldn't meet them. Not yet. There is something almost, I want to say, admirable, though that's not quite the right word for a piece of physics. Admirable implies effort, and physics doesn't do effort. Something almost trustworthy about that. A conjecture that knows what it would take to be wrong. The question is whether the universe is going to show us. Stars spend their lives making things heavier. Hydrogen becomes helium in the core, helium becomes carbon, carbon becomes oxygen, and the chain continues: neon, magnesium, silicon, sulfur. Each step releasing energy, each step building a nucleus slightly more bound than the last. This is what stellar fusion is, at its mechanical core, a long, slow search for the configuration where the strong nuclear force has done the most work, where the protons and neutrons are packed in the arrangement that holds together with the least leftover energy, where the nucleus has settled as far down as it can go. That search ends at iron. Iron 56, 26 protons, 30 neutrons, the particular arrangement the universe keeps arriving at when stars run out of lighter things to burn, has a binding energy per nucleon of approximately 8.8 mega-electron volts. That number is, within ordinary nuclear physics, a kind of flaw. Fusing iron into something heavier costs energy rather than releasing it. Splitting iron into something lighter also costs energy. The nucleus sits at a local minimum so deep that almost nothing in ordinary stellar physics can push it further down. When a massive star's core accumulates enough iron, fusion stops, the energy source turned off, and what follows, the collapse, the shockwave, the supernova, is the universe's way of dealing with matter that has nowhere left to go. Iron is not the flashiest element. It doesn't glow with the particular blue of hot young stars or carry the romantic weight of gold. It is, if you want to be honest about it, a fairly drab metal, heavy, prone to rust, common enough that it makes up most of the Earth's core and a significant fraction of your blood. The hemoglobin carrying oxygen through your body right now contains an iron atom at its centre. Not because biology was being poetic, because iron is stable, available, and good at holding on to things. It is the practical choice. For most of the history of nuclear physics, iron's reign over stability was simply assumed. Not questioned, not examined closely for cracks, just accepted as the lower bound of what ordinary matter could achieve. If you wanted to know the most stable thing that nucleons could build, the answer was iron 56, and the answer had always been iron 56, and there was no particular reason to think that was going to change. Then someone did the calculation for strange matter. The calculation, and this is the part that deserves to be said plainly without drama, asks a simple question. What is the energy per baryons of a large chunk of strange quark matter in its lowest energy state? Not a strangelet, not a small droplet with surface effects complicating things, but bulk strange quark matter, the infinite volume limit where the edges don't matter and only the interior counts. And the answer, within the MIT bag model, for certain values of the parameters, specifically for values of the bag constant below roughly 57 mega-electron volts per cubic femtometer, and for a strong coupling constant in a range consistent with other known physics, is a number below 930 megaelectron-volts per baryon. 930 megaelectron-volts per baryon is iron's number. That is the energy carried by each nucleon in iron 56, the benchmark against which nuclear stability is measured. Strange matter, in the parameter ranges where the hypothesis holds, comes in lower. Not by much, not by the kind of margin that would make a physicist slam a table. By a few percent, sometimes less. A modest difference in absolute terms, but the direction is everything. Lower energy per baryon means more stable. More stable means that if ordinary matter had a path to become strange matter, the thermodynamics would push it that way. Iron, the patient sovereign of nuclear stability, the thing that massive stars spend millions of years building toward, iron would not be at the bottom anymore. It would be sitting one step above something quieter and denser and more settled than anything the periodic table contains. That's what the number means. Not that iron is wrong, not that nuclear physics has been doing something incorrectly for a century, but that nuclear physics may have been measuring stability within a restricted domain without fully knowing the domain had a boundary. The stability of iron is real. It is the most stable configuration of nucleons. The caveat, the small consequential caveat, is that nucleons themselves might not be the final form. This project runs without sponsors, without institutional backing, just this work and the people who find value in it. If you want to support what we're building here, the Patreon link is in the description. We're closing in on 200 members, and when we get there, we're launching a Discord, a private space for people who actually want to think about this stuff together. No noise, just curious minds. If you want that to exist, that link is how it happens. Iron didn't lose its title loudly, there was no announcement. The calculation appeared in papers that most people never read, in a corner of theoretical physics that the broader culture has still not quite noticed. Iron is still the answer to the question everyone asks, what is the most stable nucleus? Because that question technically specifies nuclei. It asks about protons and neutrons arranged in shells. It doesn't ask about quarks arranged in something that no longer has shells at all. Change the question slightly. What is the most stable configuration of strongly interacting matter? And the answer may no longer be iron. The answer may be something with no name in the periodic table, no place in the chemistry of living things, no role in the biology that evolved on this particular planet around this particular star. Iron is still here. It is still in your blood, still in the Earth's core, still the ash that massive stars leave behind. It ruled stability for as long as we knew how to look. And then, quietly, in a journal that most people have never opened, a number appeared that was slightly smaller than its number. That's all it took. A number smaller than another number. The rain didn't end with noise. It just became conditional. The radiator in the corner of the room where I first read about this was making a ticking sound, not loud, just persistent. The kind of noise that marks time without meaning to. I mention it only because there's something appropriate about that sound accompanying this particular idea. A slow, rhythmic insistence, something pressing against its own container. The Pauli exclusion principle is one of those rules in physics that sounds, on first encounter, almost administrative. No two identical fermions can occupy the same quantum state simultaneously. You read it and think, fine, yes, particles have manners. Understood, moving on. It doesn't feel like one of the load-bearing walls of reality. It feels like a footnote. It is not a footnote. Everything solid is solid because of it. The reason your hand doesn't pass through the table is not, primarily, because atoms repel each other through electromagnetic force, though they do somewhat. The deeper reason is that the electrons in your hand and the electrons in the table refuse, at a quantum mechanical level to share states. They cannot occupy the same space with the same energy and the same spin. They push back, not aggressively, just immovably. The Pauli principle is the stubbornness underneath all physical resistance, and quarks obey it too. Inside a proton you have 3 quarks, 2 up, 1 down, each carrying a different color charge, which is the quantum number that lets them coexist in the same small space without violating the exclusion rule. The color charge is, in this context, the mechanism that keeps the 3 from being truly identical. Without it, the Pauli principle would forbid the proton from existing. With it, the 3 quarks stack into the lowest available states, and the proton holds together. Now imagine not 1 proton but many, a chunk of nuclear matter, large enough that you're thinking about it as a bulk substance rather than individual particles. Inside that chunk you have a sea of up quarks and a sea of down quarks, all trying to occupy the lowest energy states available to them. The lowest states fill quickly, the next ones fill, and as you add more quarks, as the density increases, as you press the matter harder, the new quarks have nowhere to go except higher. The lower levels are taken. The only available real estate is up, in energy terms, and so the quarks climb, and the overall energy of the system rises with them. This is called degeneracy pressure. The pressure created not by temperature, not by particles bouncing off each other in the classical sense, but purely by the Pauli principle's refusal to let fermions share. It is a cold pressure, a quantum pressure, a pressure that exists even at absolute zero, because it comes from identity rather than motion. You can cool the matter down as far as physics allows, and the pressure remains, because the quark still can't share states. In ordinary nuclear matter, this pressure operates across 2 flavors. Up quarks fill their levels, down quarks fill their levels. The 2 populations are distinct, different flavor quantum numbers, different states, so they don't compete directly with each other. But they are each independently running out of room. The up quarks are crowded, the down quarks are crowded, and the overall energy of the system carries the signature of that crowding, higher than it might need to be, if, and this is the operative word, if there were more room. Think of it as a building with 2 floors. The ground floor fills first, then the second floor fills. New arrivals, new quarks, as the density increases, have to go to the 3rd floor, which doesn't exist in 2-flavor matter. There is no 3rd floor. There are only 2, and both of them are getting full, and the energy climbs because there's nowhere lower left to go. Strange matter has a 3rd floor. When strange quarks are present alongside up and down quarks, in roughly equal proportions in a deconfined state where the quarks are not locked into individual nucleons, a 3rd population appears. Strange quarks carry their own quantum numbers. They don't compete with up or down quarks for the same states. They open a new set of levels, a new floor previously unavailable. And what happens when a new floor opens in a crowded building is, well, the crowd spreads. Some of the quarks that were pushed into higher energy states on the first 2 floors can redistribute. Not literally. Not by moving, this is quantum mechanics. The language of moving is already strained here. But the system finds a new equilibrium, and in that equilibrium the average energy per quark is lower than it was before. The 3rd floor isn't just additional space, it's relief. The quarks don't have to climb as high. The degeneracy pressure is not gone, it's never gone. The Pauli principle doesn't turn off, but it's reduced. Distributed across a larger state space, and the total energy of the system per unit of matter drops. That drop is the stability argument. Not all of it. There's also the question of whether producing strange quarks costs more energy than the redistribution saves, which is where the bag constant enters and the calculation becomes parameter dependent. But the directional logic, the reason 3 flavors could in principle be more stable than 2, is right here, in the crowding, in the relief of the 3rd floor. I want to be careful not to make this sound more inevitable than it is. The 3rd floor opening up doesn't automatically make strange matter stable. It makes it possible that strange matter is more stable, which is a different claim. The actual stability depends on a competition between the energy saved by spreading across 3 flavors and the energy spent producing the heavier strange quarks, and that competition has no clean winner without precise knowledge of parameters the field is still measuring. The direction of the effect is clear. The magnitude is not. But the direction matters enormously because the direction is what the hypothesis rests on. The Pauli pressure argument is not a rumour or a fringe interpretation. It is a straightforward consequence of quantum statistics applied to a 3-flavor quark system. The logic is solid. The question is whether the numbers, when measured precisely enough, will confirm that the effect is large enough to bring strange matter below ordinary matter's energy level. And that's the thing that makes this feel. I keep wanting to find a word that isn't quite wonder, not quite unease, that makes this feel weighty. The mechanism is not exotic. It's the same exclusion principle that makes tables solid and metals conductive and white dwarf stars supported against collapse. The same rule, applied 1 flavor wider, produces a system that might be more stable than everything we've ever touched. Not through some new physics, not through a force we haven't discovered, through the same stubbornness that keeps your hand from passing through the table, extended by 1. The room turns out to be larger than the building suggested from outside. Ordinary matter built its architecture on 2 floors and called it finished. Strange matter, if it exists, if it forms, if the numbers fall the right way, found a staircase that ordinary matter never climbed. Not because ordinary matter is wrong, because 2 floors was all it ever needed to know about. The 3rd floor was always there. The quarks just never had a reason to go looking for it. Under normal conditions, in the low-pressure, low-density world where protons and neutrons hold their shape, strange quarks decay too quickly to accumulate. The 3rd floor stays empty, and an empty floor is, for all practical purposes, the same as no floor at all, except in the accounting, in the energy budget, in the quiet arithmetic of what is possible versus what has formed. The universe keeps a very careful ledger. Outside somewhere a car passes. The sound arrives and recedes in about 4 seconds, which is long enough to follow if you're paying attention and short enough to miss entirely if you're not. 4 seconds of ordinary matter moving through ordinary space, and every atom in that car, every proton, every electron, every quark locked into its 2-flavor arrangement, is doing exactly what it has been doing for the entire age of the universe. Holding. The question of why is more interesting than it first sounds. If strange matter is more stable than ordinary matter, if the energy per baryon genuinely sits lower in the 3-flavor configuration, then there is a real sense in which everything around you is not at the bottom. The protons in your body, the neutrons in the iron at the Earth's core, the hydrogen in the sun, all of it carrying slightly more energy than the universe's most stable configuration, all of it sitting, in the thermodynamic language, above a lower valley it has never found. This should bother you, at least a little. Not because the danger is immediate, it isn't, and the rest of this chapter is partly about why, but because the situation it describes is genuinely strange. A universe full of matter that is, in a precise and non-metaphorical sense, still falling. Imperstably, or perhaps not falling at all, not ever, because the path down is blocked by something that has held without effort for 13 billion years. That something is called an energy barrier. The concept is not exotic. You encounter it without knowing the name every time you light a match. Wood is chemically unstable in the presence of oxygen. The products of combustion, carbon dioxide and water, sit at a lower energy state than the reactants. Wood wants to burn in the thermodynamic sense that the universe wants things to move toward lower energy. But wood doesn't spontaneously combust at room temperature because the reaction requires an activation energy, a small energetic push to get the process started, to break the initial bonds and let the lower energy pathway open. The match provides that push. Without it, the wood sits indefinitely in a higher energy state that it could theoretically leave but practically cannot. The barrier between ordinary matter and strange matter is something like that activation energy, except enormously, almost incomprehensibly higher. To understand why, you have to think about what the conversion would actually require. A proton contains 2 up quarks and 1 down quark. For that proton to become part of strange quark matter, strange quarks need to appear. Strange quarks don't arise from the strong force. The strong force binds quarks together, but doesn't change their flavor. Flavor change requires the weak nuclear force. Specifically, it requires the weak interaction to convert a down quark into a strange quark, which happens via the emission of a virtual W boson and produces, briefly unstably, a strange baryon like the lambda particle, which then decays back into ordinary matter in about 10 to the power of minus 10 seconds under normal conditions. This is the fundamental problem. A single quark converting to strange is not energetically favorable in isolation, because the strange quark is heavier than the down quark, and the lambda is heavier than the nucleon. You are moving uphill to get to a system that is only lower in energy when you have enough strange quarks present simultaneously. One conversion doesn't help. A few conversions don't help. You need a large number of quarks. Estimates vary, but the threshold for stability is thought to require baryon numbers in the hundreds or thousands at minimum to convert to strangeness nearly simultaneously, so that the collective energy saving from the 3-flavor configuration outweighs the individual cost of each conversion. And nearly simultaneously means within a timescale set by the weak interaction rate, which is slow, profoundly slow by the standards of nuclear physics. The weak force is weak for a reason. Its carrier bosons, the W and Z, are heavy, and the interaction probability falls off steeply. At the energies and densities found in ordinary matter under ordinary conditions, the probability of even 2 or 3 quark flavor conversions happening simultaneously in the same nucleus is vanishingly small. The probability of hundreds happening in the same nucleus within the required window is, it is not 0 technically, but it is a number so close to 0 that writing it down would require an exponent that would take longer to read than the age of the universe. This is why we are still here. Not because the barrier is a wall in the intuitive sense, not because the universe has posted a guard, but because the only path from ordinary matter to strange matter at low density and low temperature runs through a sequence of events whose joint probability is so catastrophically small that it has not occurred spontaneously anywhere in the observable universe in 13 billion years. Not in your body, not in the Earth's core, not in the hearts of ordinary stars. The barrier holds not through strength but through sheer improbability. There is something, I want to call it uncomfortable, though that might be the wrong register, something quietly vertiginous about this. The safety of ordinary matter is not built on permanence, it is built on statistics, on the near impossibility of the right sequence of events assembling itself without help. The atoms in the car that just passed outside a stable the way a long odds lottery is unlikely to be won. Not because winning is forbidden, but because the conditions that produce a win are so specifically demanding that they almost never arise. Almost. The qualifier matters, because the barrier can be crossed. Not spontaneously, not in your kitchen or in the atmosphere or in the rock beneath your feet, but in places where the conditions are not ordinary, where the density is high enough that quark flavors mix freely, where the weak interaction doesn't have to work against the grain because the energy scales have shifted, where the barrier, which looks impassable from here, might look different from inside. Those places exist, or may exist. And the question of what happens there, whether strange matter actually forms, whether it persists, whether it can survive long enough to mean anything, is a separate question from the one this chapter is holding. This chapter is only asking why we haven't collapsed. The answer is the barrier. The barrier is real, it is tall, it is made of improbability rather than prohibition, and it has held. But here is where the word luck starts to feel like the right word, rather than a rhetorical convenience. Luck implies contingency. It implies that things could have gone differently, that the outcome was not determined by necessity, but by the particular arrangement of circumstances that happened to obtain. And the stability of ordinary matter is, in a real sense, contingent. It depends on the strange quark being heavy enough and the weak interaction being slow enough and the threshold for strange matter stability being high enough. That spontaneous conversion has not occurred in 13 billion years. Change any of those parameters significantly, make the strange quark lighter, make the weak force faster, lower the stability threshold, and the calculation shifts, the barrier shrinks, the improbability decreases. The universe we would have inherited would be different, perhaps radically, perhaps not there to be inherited at all. We exist in the parameter range where the barrier held, where the numbers came out in favor of two-flavor matter, persisting long enough for stars to form and planets to cool, and chemistry to find its way to biology, and biology to find its way to something that could notice the barrier and wonder about it. That's not nothing. It is, depending on how you hold it, either the most ordinary fact in the world. Of course, the universe we find ourselves in permits our existence. We wouldn't be here to notice otherwise, or one of the more quietly staggering ones. 13 billion years, the barrier holding. Every proton in every atom you've ever touched, sitting above a lower valley it has never found, separated from it by a sequence of events whose probability is essentially zero. Not zero. Essentially zero. The distinction between those two things is where we live. At 3,000 members, this project shifts to human voiceover permanently. If you want to be part of making that happen, the doors are open and the link is in the description. The barrier will probably hold tonight, and tomorrow, and for longer than any timescale that matters to anything made of ordinary matter. The question of whether it holds forever, whether somewhere in the universe, under conditions that don't exist here, it has already been crossed, is a different question entirely. That question has an address. A very specific, very dense, very quiet kind of address. There is a particular quality to the light at a certain hour of the night, not dark exactly, not the full dark of deep sleep, but the dim grey of a room where the last lamp has been off long enough that your eyes have adjusted, and everything has settled into its approximate shape. Objects become suggestions of themselves. You know what the chair is, you know roughly where it sits, but you're working from memory as much as observation, filling in the details from what you already know rather than from what you can currently see. That is roughly the epistemic situation with Strangelets. A strangelet, it's... The word arrived from a 1984 paper and stuck. The way informal names in physics sometimes do, is a small droplet of strange quark matter. Not the bulk substance, not a strange star, not the interior of some massive compressed object, but a small piece, a fragment, something with a finite number of quarks, a surface, a charge, a size, something that, if it exists, would be discrete and countable rather than continuous. An object in the ordinary sense of the word, except built from deconfined quarks rather than from the nucleons that objects are usually built from. What would it look like? The honest answer is that nobody knows, because nobody has seen one. What it would look like is derived in the way that many things in theoretical physics are derived, from the properties of its constituents, from the equations that govern its interior, from the boundary conditions imposed by having a surface and a finite volume. The picture that emerges is not a picture exactly. It's more like a description of something seen in very low light. A small strangelet, baryon number in the range of a few to a few hundred, would be positively charged. This is a consequence of the mass difference between strange and down quarks. Because strange quarks are heavier, a strangelet in equilibrium carries a slight deficit of strange quarks relative to the perfectly balanced bulk, which shifts the charge balance away from neutrality and toward positive. The charge scales roughly as the baryon number to the 2/3 power. Larger strangelets are more positive in absolute terms, less positive per unit of matter. And for very large strangelets, the charge behavior can shift again, with some theoretical calculation suggesting negative charge in certain regimes, though that prediction is more uncertain and more model-dependent than the small strangelet result. Size. A strangelet with baryon number 100 would be, this is an estimate, dependent on the density of strange matter, on the order of a few femtometers across. A femtometer is 10 to the power of minus 15 meters, the scale of atomic nuclei. At baryon number 100, a strangelet would be comparable in size to a medium nucleus. Denser, though. Strange quark matter is thought to be somewhat denser than nuclear matter, the quarks packed more tightly without the nucleon structure imposing its own length scale. A strangelet is not heavy by human standards. Baryon number 100 means a mass on the order of 10 to the power of minus 22 grams, but it is extraordinarily dense for its size. Stability is the harder question, the one the chapter summary promised not to resolve and won't. In bulk, strange matter might be stable, that is the Bodmer-Witten conjecture, and it remains unproven. But bulk matter and small droplets are different. Surface effects matter at small sizes. The quarks near the surface of a strangelet are in a different environment than the quarks in the interior. They experience a boundary which costs energy, which raises the energy per baryon above the bulk value. The smaller the strangelet, the larger the fraction of quarks that are near the surface, and the more this surface energy dominates. Below some critical baryon number, estimates vary widely, from tens to thousands depending on assumptions about surface tension. The surface penalty outweighs the stability advantage of the three-flavor configuration. Small strangelets would be unstable even if bulk strange matter is stable. There is a window somewhere, a minimum size above which, if the hypothesis holds, a strangelet becomes self-sustaining. Below that size, it decays. Above it, it persists. Where that window sits is not known. Whether it sits anywhere is not known. This is where the fossil species feeling comes from, I think. Not the uncertainty about whether strangelets are stable. That uncertainty is just uncertainty, clean and straightforward. It's the quality of the description itself. The way the object can be characterized in detail, a charge, a size, density, surface behavior, stability conditions, without any of that characterization being grounded in direct observation. The way the properties are real properties, derived from real physics, pointing at a real thing, but the real thing has never been found. A paleontologist describing a species from bone fragments alone still knows things. The bone tells you about diet, about locomotion, about proximate size and probable posture. The description is not invented. The animal was real, but the description and the animal are separated by time and absence in a way that makes the knowledge feel different from knowledge of something you can currently point at. Strangelets are separated from their description not by time, but by the gap between theory and observation, between derivation and detection. The properties exist in the equations. Whether anything in the universe has those properties and is present enough to find, that is the part the equations cannot answer. Searches have been conducted at particle accelerators, in cosmic ray detectors, in analyses of samples of ordinary matter looking for anomalously heavy nuclei that might be strangelets acquired, an electron shell, and gone unnoticed. Nothing confirmed. Some candidates over the years that didn't survive scrutiny. The searches place upper bounds. There can't be too many strangelets in cosmic rays, or they would have been detected by now, but upper bounds are not absences. They are limits on abundance, not proof of non-existence. The chair is still there in the dark room. You know its shape, you know where it sits. You're just not currently looking at it in a way that confirms it. Strangelets are, at this moment, objects that the universe may contain and that we have not yet learned to see clearly. Not proven absent. Not confirmed present. Real, possibly. Here, possibly. Waiting in the low light of a hypothesis that has been running for 40 years without resolution, described in enough detail to feel like knowledge and not yet confirmed enough to be certain. Cat's Cradle was published in 1963. In it, Kurt Vonnegut described a fictional substance called Ice-9, a polymorph of water with a melting point of 45.8 degrees Celsius, solid at room temperature, and capable of converting any liquid water it contacted into more of itself. A single crystal dropped into the ocean would freeze the ocean, not through temperature, not through a chain reaction of cooling, but through direct physical contact, the seed imposing its structure on everything it touched. One molecule at a time, each new crystal becoming another seed, the process ending only when there was no liquid water left to convert. Vonnegut was writing satire. He was not writing physics. But when physicists, in the years following Witten's 1984 Conjecture, began seriously working through what would happen if a sufficiently large, sufficiently stable strangelet contacted ordinary nuclear matter, the structure they found was not identical to Vonnegut's image, the mechanisms are completely different, but shaped similarly enough that the reference has persisted in the literature for 4 decades. Not as a joke, as a shorthand for a specific thermodynamic logic that is worth understanding precisely, because it is only by understanding it precisely that you can evaluate how seriously to take it. The coffee in whatever cup is near you right now has gone cold. The ceramic is room temperature, the kind of temperature where nothing dramatic happens to matter, where the atoms in the mug and the atoms in the cooled coffee and the atoms in the air above it are all doing exactly what they have been doing for hours without anything converting into anything else. That ordinariness is the baseline. Hold it. Now, a strangelet, negatively charged, with a baryon number above whatever critical threshold makes it stable. Not a small one, a large one, one that has survived long enough to be a genuine piece of bulk strange matter with a surface and a charge and a specific interaction profile, arrives in contact with an ordinary nucleus. What happens? The negative charge matters first. A positively charged strangelet would be electrostatically repelled by the ordinary nuclei, which are also positively charged. The Coulomb barrier between them would need to be overcome before any contact occurred, and at the energies and temperatures of ordinary matter, that barrier is generally prohibitive. Most strangelets, according to the theoretical calculations, would be positively charged. And that positive charge is one of the reasons physicists are not lying awake at night worrying about this scenario. But for large strangelets, in certain theoretical regimes, the charge can go negative. A negatively charged strangelet is not repelled by ordinary nuclei. It is, in fact, attracted to them. The nucleus makes contact with the surface of the strangelet. At the surface, the nuclear matter encounters a region of deconfined quarks sitting at a lower energy state than the nucleons in the nucleus. The strong force doesn't stop at the boundary and it operates across it. The quarks in the nucleus and the quarks in the strangelet interact. And because the interior of the strangelet represents a lower energy configuration than the nucleon structure of the incoming nucleus, there is a thermodynamic gradient. Energy flows downhill. The quarks from the nucleus, the up and down quarks that were organized into protons and neutrons, deconfine at the boundary, enter the strangelet's quark sea, and the system finds equilibrium by producing strange quarks via weak interactions to balance the flavor content. The nucleus has been absorbed. The strangelet is now slightly larger. The energy released in this process, the difference between the energy of the ordinary nuclear matter and the lower energy of the strange matter it became, is deposited as heat at the surface. The conversion is exothermic. Energy comes out, and a larger strangelet, with more surface area, can absorb more nuclear matter per unit time. The process, once started, is self-accelerating. Not explosively, the rate is limited by how quickly nuclear matter can reach the surface, and by the weak interaction rates needed to produce strange quarks, but directionally irreversibly, a strangelet that begins growing has a thermodynamic incentive to keep growing. This is the ICE-9 structure, not the mechanism. The mechanism is quark deconfinement and weak interaction-driven flavor equilibration, not molecular rearrangement, but the logic. A seed of lower energy matter in contact with higher energy matter, converting the higher to the lower, growing in the process, the growth providing more surface for more conversion. The arrow points one way. There is no thermodynamic pathway back. Strange matter, once formed at sufficient scale from ordinary matter, does not spontaneously revert to ordinary matter, because reverting would mean moving uphill in energy, and systems do not spontaneously move uphill. I want to be careful here. Careful in a way that the scenario sometimes doesn't get in popular treatments, because the physics argument is genuinely worth separating from the horror framing that tends to accompany it. The ICE-9 scenario is not a prediction. It is a logical consequence of the premises, and the premises themselves are uncertain. Strange matter stability is not confirmed. Large negatively charged strangelets are not confirmed to exist. The charge distribution of strangelets in the parameter range where stability holds is not fully settled. Each of those uncertainties is a real gap in the chain of reasoning required for the scenario to operate. But, and this is the part that deserves its own sentence, and probably its own silence after it, the physics of the conversion mechanism itself, conditional on stable negatively charged strangelets existing, is not speculative. If the premises hold, the thermodynamic logic follows. The exothermicity is real, the irreversibility is real, the self-amplification is real. The scenario does not require new physics or exotic assumptions. It requires only that the strange matter hypothesis be correct and that the charge conditions be met. That is a different thing from saying it is likely. It is a statement about the structure of the argument. The scenario is either impossible because the premises fail, strange matter is not stable, or stable strangelets are always positively charged, or it is possible in a way that has no natural stopping point. There is no middle option where the conversion starts and then stalls. The thermodynamics doesn't offer a partial version. If a sufficiently large, negatively charged strangelet contacted ordinary matter under the right conditions, the process would not stop at a polite boundary and wait for permission to continue. The planet becomes a hot, dense sphere of strange matter, roughly the size of a large city, because strange matter at nuclear density is far more compressed than the ordinary rock and ocean and atmosphere it would replace. The object that remained would be stable, absolutely stable, in the thermodynamic sense, nothing left to convert, nowhere lower to go. Vonnegut's ocean freezes, just not with water. The reason physicists take this argument seriously enough to write papers about it, not as a prediction, but as a scenario to formally evaluate and constrain, is that physical arguments with clean internal logic and catastrophic conditional consequences deserve careful treatment, even when the conditions seem unlikely. You don't dismiss a scenario because the premises are uncertain. You examine the premises, you test them, you look for observational constraints that can bound the possibility, and you report what you find honestly. What they found, and what the next chapter is about, is that the universe has already been running this experiment for a very long time on objects much larger than any accelerator. The results are on balance reassuring. On balance. The moon has no atmosphere worth measuring. A thin scattering of atoms, sodium, potassium, traces of other elements, clings to its surface at pressures so low that the word atmosphere becomes almost honorary. There is no weather, no magnetic field substantial enough to deflect incoming particles, no ocean to absorb and distribute energy. The surface sits exposed directly to everything the universe sends in its direction, and the universe sends quite a lot. Cosmic rays arrive continuously. High-energy protons, atomic nuclei stripped of their electrons, particles accelerated to significant fractions of the speed of light by supernovae and pulsar winds, and the shock fronts of distant violent events. They travel through interstellar space, and they arrive at the moon's surface, and they strike the rock there with energies that dwarf anything produced in particle accelerators on Earth. The moon has been receiving this bombardment for approximately 4.5 billion years, without pause, without protection. Every square meter of lunar surface has been struck by cosmic rays more times than there are atoms in a grain of sand. Some of those cosmic rays carry enough energy to produce, in their collisions with lunar rock, the kinds of particle interactions that physicists study in accelerators. Strange quarks are produced in high-energy collisions routinely. They're not exotic in that sense, not rare products of specially tuned experimental conditions. They appear whenever the collision energy is sufficient, and sufficient energies arrive at the moon's surface every second, have arrived every second for 4.5 billion years. If stable strangelets can be produced in high-energy collisions, and if they are negatively charged, and if negatively charged strangelets absorb ordinary matter the way the thermodynamic argument suggests, then the moon is precisely the kind of place where the scenario should have played out by now. The conditions are better than any accelerator. The exposure time is incomparably longer. The absence of atmosphere means no interference, no absorption of incoming particles before they reach the target. The moon is, in the language of experimental physics, an extraordinarily well-exposed detector with a 4 billion year integration time. The moon is still there, still made of ordinary matter, still reflecting sunlight in the same way it always has, still occupying its orbit, still the same object that formed from the debris of an ancient collision, and has been cooling and sitting ever since. The Apollo missions brought back rocks, ordinary rocks. The samples have been analysed in detail, not specifically for strangelets, but their mineralogy and isotopic composition are consistent with normal nuclear matter that has been subjected to cosmic ray bombardment without being converted into anything else. This is the argument. It doesn't require equations. If the scenario worked, if stable negatively charged strangelets were produced in cosmic ray collisions and then proceeded to absorb surrounding matter, the moon would not look the way it looks. It might not exist in any recognizable form. The process, once started, has no thermodynamic break. 4.5 billion years is an extraordinarily long time for a runaway conversion to not have run away. The argument was made formally and carefully by Jaffe, Busse, Wilczek and Sandweiss in their 2000 review of speculative disaster scenarios at RHIC. They didn't invent it. The logic is straightforward enough that several people had noted it independently, but they made it rigorous. The moon argument and versions of it involving the sun and the dense stars provides what they called empirical bounds, not theoretical constraints on what the physics allows, but observational constraints derived from the continued existence of objects that should have been affected if the scenario operated. The bounds are strong, uncomfortably strong in the sense that they leave very little room for the dangerous version of the strangelet hypothesis to operate. Either stable strange matter doesn't exist, or it always carries positive charge and is repelled by ordinary nuclei, or the production rate in cosmic ray collisions is so low that 4.5 billion years of lunar bombardment has simply never produced a dangerous one, or some combination of these. The moon's continued existence doesn't prove which of these is true. It constrains the space of possibilities. There is something almost, I keep reaching for a word and finding only almost, something almost quiet about this kind of evidence. It doesn't arrive in a paper with a striking title. It doesn't require a new instrument or a novel technique. It just requires looking at the moon and asking how long it has been there and what it has been exposed to and what it would look like if the scenario were real. It would look different. It doesn't. That's the argument. The whole argument. A world that has been sitting in the line of cosmic fire for longer than complex life has existed on Earth, and is still, as of tonight, exactly what it appears to be. The scenario is not ruled out. The moon argument constrains it, boxes it, reduces the viable parameter space significantly, but it doesn't close the door. The door Witten described in 1984 is still standing. The moon is simply one of the better reasons to think it might be locked. Might. Somewhere tonight, there is an object roughly 10 kilometers across that contains more mass than the sun. Not approximately, not poetically. The number is real, the object is real, the 10 kilometers is a genuine physical dimension. Smaller than most cities, smaller than the distance between two highway exits, and inside it, matter exists in a state that no laboratory on Earth has ever replicated, that no instrument has ever directly sampled, that theory can approach but not quite reach. The object sits in its place in space doing nothing dramatic. It is not exploding, it is not collapsing further. It is simply being what it is, under conditions that have no equivalent anywhere in ordinary experience. Pressure is a word that understates itself in this context. In ordinary matter, pressure is what you feel when something pushes against you. The atmosphere pressing down, water pressing inward when you dive, the slow weight of rock on rock in the deep earth. These are pressures measured in pascals or atmospheres or bars, and the largest of them, the pressure at the center of the earth, roughly 360 gigapascals, is enough to compress iron slightly and force exotic mineral phases that don't exist at the surface. Geologists study these pressures with diamond anvil cells, squeezing tiny samples between the points of two diamonds to reproduce what the Earth's core does passively and continuously. The pressure at the center of the densest stellar objects is approximately 10 to the 34th pascals. The center of the Earth, at 360 gigapascals, is 3.6 times 10 to the 11th pascals. The difference between these numbers is not a matter of degree, it is a matter of kind. At pressures 22 orders of magnitude beyond anything the Earth's interior produces, matter does not behave like matter. The concepts that describe ordinary compressed substances, elastic deformation, phase transitions between solid and liquid, the rearrangement of atoms into denser crystal structures, these concepts have no purchase. There are no atoms in the sense of nuclei surrounded by electron shells. The electrons were long since incorporated into the nuclear matter. The nuclei themselves, under sufficient pressure, may not survive as discrete objects. This is where the quark structure of matter stops being theoretical background and starts being the only description available. Under pressures high enough, nucleons, the protons and neutrons that survive every ordinary condition in the universe, are compressed into proximity so extreme that the boundaries between them become ambiguous. The quarks inside one nucleon overlap with the quarks inside its neighbour. The individual identity of the nucleon dissolves. What remains is a sea of quarks, deconfined, moving through a shared volume rather than locked into the specific three-quark arrangements that define ordinary nuclear matter. This state, quark matter, deconfined, dense, is what theory predicts exists somewhere in the interior of the densest stellar objects. Whether it is strange quark matter is the open question. The argument for strangeness follows from the same logic as before, but with the energy barrier removed. At sufficient density, the weak interaction rates increase. The strange quark mass, which at low density makes producing strange quarks energetically costly, becomes less significant relative to the chemical potential of the system, the energy per quark in an extremely dense medium. The condition that makes ordinary matter metastable at low density, the near impossibility of simultaneous quark flavor conversion, relaxes at high density because the quarks are already so close, already so frequently interacting, that the weak processes required for flavor equilibration can actually proceed on timescales relevant to the system. The barrier that has held ordinary matter in its current configuration for 13 billion years is not a universal barrier. It is a low-density barrier. In the interior of sufficiently dense objects, it may not exist at all, which means that if strange quark matter is more stable than ordinary matter, if the Bodmer-Witten conjecture is correct, then the interior of the densest stellar objects is not merely a place where strange matter could form, it is a place where strange matter should form, where the thermodynamics actively favours the three-flavour configuration and the conditions permit the transition that ordinary matter, sitting in the low-density universe, can never make. There is something worth sitting with in the present tense of this, not in the past, not in some early universe phase transition, not in a hypothetical future, but now, tonight. While you are lying still and the room around you is doing nothing remarkable, somewhere in the observable universe, inside one of the hundreds of millions of dense stellar objects that exist in the Milky Way alone, matter may be sitting in a configuration that ordinary matter has been trying to reach for the entire age of the universe. The three-flavour equilibrium, the lower valley, the true ground state if there is one, expressed not in an equation or a conjecture but in actual quarks, actual densities, actual physics operating without the barrier that protects ordinary matter from itself. The object doesn't know this. The pressure doesn't intend anything. These are not purposive things. Pressure doesn't want to reduce strange matter the way a river wants to reach the sea. The pressure simply is. The density simply exists. And within that existence, the physics follows the same rules it follows everywhere, except that here, unlike almost everywhere else in the universe, the rules permit something that the rules elsewhere forbid. The barrier that time cannot cross, pressure crosses. Not quickly, not violently, not in a way that produces light visible from here, just the conditions are different. The outcome permitted by those conditions is different. And in the interior of an object 10 kilometers across that contains more mass than the Sun, the permitted outcome may already be the actual one. Whether strange matter once formed in such an interior tells us anything, whether it produces signatures detectable at distance, whether it affects the object's behavior in ways that instruments can measure, whether the universe has been showing us strange stars all along without our having the tools to recognize them. That is a question the chapter holds without trying to answer. The conditions exist, or may exist. That much the physics allows. What exists inside them is still being listened for. In the constellation Scorpius, roughly 8,150 light-years from here, there is a compact object at the center of a supernova remnant called Hesj 1731-347. The remnant itself is unremarkable in the catalogue sense, a shell of expanding debris from a stellar death, glowing in X-ray and radio wavelengths, moving outward at speeds that allow astronomers to estimate its age at somewhere between 2,000 and 6,000 years. What sits at its center is less easy to categorize. The object's mass has been estimated at 0.77 solar masses, with an uncertainty range of roughly plus 0.20 and minus 0.17 solar masses. Its radius has been estimated at 10.4 kilometers, with an uncertainty of about plus or minus 0.8 kilometers. These numbers come from a 2022 analysis published in Nature Astronomy by Viktor Doroshenko and colleagues at the University of Tübingen, who used X-ray observations accumulated over 6 years from the XMM Newton and Suzaku Space Observatories, combined with precise distance measurements from the Gaia satellite that revised the object's distance downward from earlier estimates. The numbers are the problem. Neutron stars form when the iron core of a massive star collapses under its own gravity during a supernova. The physics of that collapse, the interplay of gravity, nuclear forces and neutrino pressure, sets a lower limit on the mass of the resulting object. Current stellar evolution models place that lower limit at roughly 1.1 to 1.2 solar masses, depending on assumptions about the progenitor star's composition and the details of the collapse mechanism. Objects below that mass, within the standard picture of how neutron stars form from iron cores, should not exist. 0.77 solar masses sits well below that limit. The Tübingen team was careful about this. Careful in a way that scientific papers sometimes are when the finding is genuinely unusual, precise about uncertainties, explicit about alternative explanations, measured in tone. They noted that the measurement, if correct, makes the central compact object either the lightest neutron star ever observed or something else, something whose internal composition differs from ordinary neutron matter in a way that the standard formation models don't account for. They named one possibility, strange star. A strange star. An object composed entirely or predominantly of strange quark matter rather than neutron matter would have a different equation of state than a neutron star. The equation of state is the relationship between pressure and density inside the object, and it determines the mass-radius relationship, how large an object of a given mass can be. For neutron stars, this relationship is constrained by nuclear physics, and the constraints produce a population of objects within certain mass and radius ranges. For strange stars, the equation of state is different. The self-bound nature of strange quark matter, which doesn't require gravity to hold it together at nuclear densities, produces a different mass-radius curve, one that extends to lower masses than neutron star models comfortably allow. The mass and radius of the central compact object in Hess J 1731-347 sit in a region of the mass-radius diagram that strange star equations of state can reach, and that standard neutron star equations of state struggle to reach. Struggle, not cannot. The paper does not claim impossibility. Some exotic neutron star models, those with unusual compositions, early phase transitions, specific parameterizations, can produce objects in that mass range. The measurement does not uniquely select strange matter. It selects a region of parameter space where strange matter is one of the more natural explanations, and where ordinary neutron matter requires special conditions to be present at all. The animations you are watching were made specifically for this topic, every visual built for this episode. When we reach 1,000 members on Patreon, we are moving to a more advanced animation format that brings in actual infographics as well, for everyone who loves having the visuals match the depth of the science. If that version of this project sounds like something worth supporting, the link is in the description. The object sits in its remnant 8,150 light-years away and does not clarify anything. It emits X-rays at a temperature and luminosity that the observatories measured and the models are still working through. It has a companion star, a post-asymptotic giant branch star, likely the surviving member of the binary system whose more massive partner exploded, whose properties helped constrain the distance estimate that made the low-mass measurement possible. The whole system is real, the measurements are real, the anomaly is real. What the anomaly means is not settled. There is a version of this finding that future observations will explain within the standard picture. Better distance measurements shifting the mass upward, revised models of unusual neutron star formation accommodating the low value, some combination of factors that returns Hess J1731-347 to the category of strange but explicable neutron star. That version is possible. Most anomalies in astrophysics, examined closely enough, resolve into edge cases of known physics rather than evidence of new physics. The history of the field supports patience over excitement. And there is another version, one where the mass holds up under scrutiny, where the radius constraint tightens rather than loosens, where the equation of state that best describes this object remains in the region that strange star models occupy and neutron star models reach only awkwardly, where the sky, examined with better instruments for another decade, returns measurements that the standard picture continues to struggle with. That version is also possible. The object doesn't know which version it is. The sky doesn't offer a preference. The remnant expands at the same rate regardless of what sits at its center, and the X-rays arrive at the same detectors, whether the source is a strange star or an unusually light neutron star or something that current models haven't fully imagined yet. This is what it looks like when observation and theory are in genuine conversation, not the clean narrative of a discovery confirmed, not the equally clean narrative of a hypothesis ruled out, but the slow, unresolved back and forth of a measurement that doesn't fit neatly, and a set of models that are doing their best to accommodate it. The conversation is ongoing. The papers are still appearing. The distance measurements are still being refined. Somewhere in Scorpius, the object continues to cool. It has been cooling for somewhere between 2,000 and 6,000 years. By the time its light left for Earth, the remnant was already centuries old. By the time that light reached detectors on XMM Newton, everything that caused the explosion was long finished, and what remained was the compressed, quiet thing at the center, whatever it is, sitting in the dark at temperatures that are, by stellar standards, dropping towards silence. The sky hasn't answered. It has simply shown us something that doesn't fit comfortably, and waited. The universe was about 10 microseconds old when it became a different kind of place. Before that moment, 10 microseconds, which is not a long time in any human sense, but is an eternity in the time scale of the universe's first second, the contents of space existed as a quark-gluon plasma. Not atoms, not nucleons, not even the precursors of nucleons in any organized sense. Just quarks and gluons moving freely through a medium so hot and dense that the confinement mechanism of the strong force, the property that normally locks quarks inside hadrons, was overwhelmed by thermal energy. Everything was dissolved. Everything was free. Then the temperature dropped below approximately 150 mega-electron volts, which is roughly 1.7 trillion degrees Celsius, and confinement switched on. The quarks stopped being free. They found each other, up quarks and down quarks binding into protons and neutrons, the familiar two-flavor combinations that would eventually become every atom in every star and planet and organism in the observable universe. The transition was not instantaneous and not uniform. It happened across the expanding volume of the early universe as the temperature fell through the critical threshold, region by region, the way frost forms across a cold window, not all at once but progressively, the new phase nucleating and spreading. Whether this transition was sharp, a genuine first-order phase transition with distinct phases coexisting at the critical temperature, or smooth, a gradual crossover with no sharp boundary, is a question that lattice QCD calculations have been working on for decades. Current evidence favours a crossover at low baryon density, which is the condition that likely applied in most of the early universe. But the QCD phase diagram is not fully mapped. At higher baryon densities, or with large leptonic asymmetries, the transition may have been sharper, and in those regions the physics of what formed during confinement may have been different from the standard picture. Witten noticed this in 1984. In the same paper that introduced the strange matter stability conjecture, he observed that if the QCD transition were first order, it would have proceeded through bubble nucleation, regions of the confined phase forming inside the still unconfined plasma, growing, eventually merging until the transition was complete. In the boundaries between these regions, as the transition proceeded, the baryon number would have been distributed unevenly. Some regions would have ended up baryon-rich, and in the baryon-rich regions, if strange quark matter were the true ground state, the conditions for strangelet formation would have been met. High density, high temperature, quark deconfinement, the three-flavor equilibration that the transition to confinement would have enabled. Strangelets in this scenario would have formed during the QCD phase transition alongside the protons and neutrons that became ordinary matter. Not as a byproduct of some exotic process, not in the cause of objects that formed later, but contemporaneously with the matter we're made of. Ancient, primordial, present from nearly the beginning, and then surviving. This is the part that requires the physics to be exact, because the survival of primordial strangelets through 14 billion years of cosmic history is not automatic. Small strangelets, in the hot early universe, would have evaporated, the thermal environment stripping quarks from their surfaces faster than the binding energy could hold them. Calculations by Alcock and Fari in 1985, and revised by Madsen and others subsequently, placed a lower limit on the baryon number required for survival. Roughly 10 to the power of 45 to 10 to the power of 52 baryons, depending on assumptions about the early universe's temperature profile and the surface properties of strange matter. These are not small objects. They are macroscopic by any measure, masses ranging from asteroid scale to something considerably larger, depending on the parameters. objects of that mass, made of strange quark matter, would be nearly invisible, not metaphorically invisible, physically, electromagnetically invisible in the way that matters for detection. A strangelet with a mass of 10 to the 20 grams and a radius of a few hundred meters, which is what the density of strange quark matter implies for that mass, would interact with ordinary matter only through gravity and through the occasional direct collision with the nucleus at its surface. Its electromagnetic cross-section, relative to its mass, would be extraordinarily small. It would pass through a galaxy, through a star, through a planet, depositing energy so slowly and so sparsely that no current detector would register it as a distinct event. It would be, in all practical observational terms, dark, massive, stable, weakly interacting with ordinary matter, ancient. These are the properties that dark matter candidates are supposed to have. The timing matters here, not emotionally, just historically. Witten's 1984 paper appeared before the particle physics dark matter program had fully crystallized around the WIMP hypothesis. The idea that dark matter might be made of new particles, weakly interacting massive particles WIMPs, produced thermally in the early universe, was not yet the dominant framework it became through the 1990s and 2000s. The Strangelet proposal and the WIMP proposal arrived in roughly the same era, from different directions, addressing the same observational puzzle. Dark matter was anomalous then, as now. The rotation curves of galaxies didn't fit. The universe's matter budget didn't close. Something was missing. Witten's proposal was that the missing something might already be inside the standard model. Not a new particle, not a new force, not new physics beyond the current framework. Just the same quarks, in a configuration that the universe permitted but ordinary matter never achieved, surviving from the first moments of cosmic history in objects too massive to evaporate and too sparse in their interactions to have been directly detected. The proposal has not become the consensus. The WIMP program dominated for decades, and though WIMPs have not been found, the absence is significant, the parameter space is shrinking, the field has moved through a range of alternatives that mostly don't include strangelets. Recent lattice QCD calculations have made the first-order phase transition less likely at low baryon density, which removes the most natural production mechanism for primordial strangelets. The 2025 reappraisal by Drago and colleagues found that with large leptonic asymmetries, strangelet production remains possible even within current constraints, and that the mass distribution of surviving strangelets could be consistent with observational limits on dark matter. The hypothesis is alive, it is not leading. And here is the thing the chapter has been approaching without quite arriving at, the thing that takes a moment to feel properly. The same substance, the same strange quark matter, the same three-flavor configuration, the same lower energy state, the same Bodmer-Witten stability argument. The substance that, as a negatively charged strangelet contacting ordinary matter, represents a one-way thermodynamic conversion with no natural stopping point, and the substance that, as a primordial relic orbiting invisibly through galaxies, might be the scaffolding that held the large-scale structure of the universe together while ordinary matter was still figuring out how to form stars. Dangerous and foundational, consuming and supporting, the same properties, stability, density, the thermodynamic preference of the universe for the lower state, that make it a potential agent of irreversible conversion, also make it a plausible candidate for the invisible mass that allowed galaxies to form the way they did. The stability is not two different things in these two contexts. It is the same thing, pointing in two directions simultaneously. I don't know how to resolve that. I'm not sure it resolves. The universe may have produced, in its first 10 microseconds, an enormous quantity of the most stable form of matter in existence. That matter may be everywhere, in the halos of galaxies, in the spaces between stars, passing through the Earth at this moment in objects too massive to deflect and too sparse in their interactions to register. Or it may not exist at all, the phase transition having been a smooth crossover that never produced the conditions for strangelet formation. The hypothesis an elegant possibility that the universe simply didn't use. The scaffolding, if it's there, is holding everything up in silence. The silence is the same either way. There is a specific kind of document that exists in institutional physics, not a research paper exactly, not a press release, not an internal memo, that occupies a strange middle space between formal scientific communication and something more like a public letter written under duress. The Jaffe-Busse-Wilczek-Sandweiss Review of 1999 is one of the more unusual examples of the type. It was published, eventually, in Reviews of Modern Physics. It has been cited hundreds of times. It is a serious piece of scientific work by 4 serious physicists. It is also, if you read it with full awareness of what it was asked to do, one of the stranger things the field has ever produced. The radiator in whatever building this was written in. I keep imagining an institutional corridor, fluorescent lights, the particular smell of a physics building that hasn't been renovated since the 1980s, was probably humming, mundane, the work of writing a formal argument that a particle accelerator would not destroy the Earth proceeds, presumably, in the same ordinary physical surroundings as any other scientific writing. The relativistic heavy ion collider at Brookhaven National Laboratory was nearly ready to begin operations in 1999. RHIC, the acronym is more manageable than the full name and the field has always used it, was designed to collide gold nuclei at relativistic speeds, producing conditions that had not existed since the early universe, studying the quark-gluon plasma that the Standard Model predicted, and that no experiment had yet confirmed. It was, by the standards of particle physics, a remarkable instrument. It was also the occasion for a public controversy that the field had not quite anticipated. Frank Wilczek, one of the 4 authors of the eventual review, and one of the physicists whose earlier theoretical work on the strong force had contributed to the case for RHIC's scientific value, had written a brief piece in Scientific American in 1999 discussing some speculative possibilities for high-energy heavy ion collisions. Among them, mentioned carefully and with appropriate hedging, was the Strangelets scenario. A reader named Walter Wagner wrote back. Wagner was persistent. The correspondence became public. The question, could RHIC produce a strangelet that then absorbed the Earth, entered the newspapers. Brookhaven's then director, John Marburger, did what institutions do when a question becomes a public question. He appointed a committee. The committee consisted of Robert Jaffe of MIT, Whit Buser of MIT, Frank Wilczek then at the Institute for Advanced Study in Princeton, and Jack Sandweiss of Yale. They were asked, in effect, to answer the question. Not informally, not with a reassuring press statement, but formally in writing, with the rigour that the subject deserved if it deserved any response at all. The question they were answering was, could RHIC produce something that ends everything? There is something worth pausing on in the fact that the question was asked formally, rather than dismissed. Not every institution, and not every committee, would have taken the step of treating a speculative disaster scenario as something requiring a serious written response. The temptation to wave it away, to issue a statement noting that no credible physicist believed RHIC posed any danger, and that the public concern reflected a misunderstanding of the science, was presumably available. That response would have been, in some narrow sense, accurate. No credible physicist did believe RHIC posed any danger. But accurate and honest are not always the same thing, and Jaffe, Boozer, Wilczek and Sandweiss chose honesty over the easier version of accuracy. They took the scenario seriously on its own terms, which means they took the strange matter hypothesis seriously, worked through the strangelet production and stability arguments carefully, evaluated the conditions required for a dangerous strangelet to form and persist and absorb ordinary matter, and then, having done all of that, explained why each step in the chain of reasoning required for catastrophe was individually unlikely, and why the combination was, for practical purposes, excludable. The argument they made was not primarily theoretical. This is the part of the review that is easy to overlook and shouldn't be. The theoretical argument that stable large strangelets are uncertain, that negatively charged strangelets are unlikely, that production in heavy ion collisions at RHIC energies was not favoured by the models, was part of the review, but the review's strongest argument was empirical. The moon, dense stars, the fact that cosmic rays carrying energies far exceeding anything RHIC could produce, had been striking these objects, striking the moon directly without atmospheric protection, for billions of years, and those objects remained composed of ordinary matter. If RHIC could produce a dangerous strangelet, cosmic rays had already been running that experiment at higher energies and longer timescales. The experiment had been running for 4.5 billion years. The results were negative. 4 separate conditions, they argued, were all required simultaneously for a dangerous strangelet scenario to operate. Large stable strangelets had to exist. Intermediate size strangelets had to be metastable. The charge along the stability line had to be negative, and intermediate-sized strangelets had to be producible in heavy ion collisions. Each condition was individually unlikely based on the available theory and the cosmic ray evidence. The joint probability of all 4 was not 0, technically not 0, but constrained to a level that made the risk negligible in any meaningful sense. They published this in Reviews of Modern Physics in 2000, not in a press release. In a peer-reviewed journal with equations, with reference, with the full apparatus of scientific communication that signals this is meant to be evaluated, challenged, built upon rather than simply accepted. I find this, and this is an opinion, not a physics statement, but I find this genuinely, I want to say admirable, though the word feels slightly off for a piece of scientific work. Admirable implies virtue, and this was more like rigour. I find it a particular kind of integrity. The authors knew the scenario was almost certainly not a real danger. They also knew that almost certainly is not certainly, and that if there was a non-negligible probability they were wrong, the consequence was not recoverable. So they did the work. They closed the argument as tightly as it could be closed, acknowledged what couldn't be fully closed, and put it in the literature where anyone could examine it. This is what intellectual honesty looks like when the stakes are hypothetically infinite. Not dismissal, not alarm, just, here is the question, here is the evidence, here is the argument, here is where the argument is strongest, and here is where it depends on assumptions we cannot fully verify. The reader can decide what to do with the residual uncertainty. The LHC, which operates at energies higher than RHIC, was reviewed by its own safety group in 2008. They reached the same conclusions by the same route, and added one observation. Collisions at the LHC would be less likely to produce strangelets than RHIC, not more, because strangelet production probability decreases with increasing collision energy in the relevant models. The machine that was more powerful was, for this specific concern, less worrying. RHIC had been operating for nearly a decade by then, without producing strangelets or any anomalous signature consistent with exotic stable matter. The empirical record was lengthening. The accelerators are still running. Gold ions still collide at RHIC. Lead ions collide at the LHC. The quark-gluon plasma has been confirmed, studied, mapped in some of its properties. No strangelets have been found. The upper bounds on strangelet production tighten with each experimental run, each null result adding to the empirical case that whatever strange matter is, it is not something these machines produce in detectable quantities. The document still exists. In the journal, in the archives findable by anyone. A formal argument that the world would not end, written because the question was asked and the question deserved an answer and the answer required work. It required 4 physicists to sit down and take seriously the possibility that they were wrong. That's rarer than it sounds. The night has gotten quieter since this began. Not silent, there is always something, a distant sound of traffic or wind, or the particular low or hum that buildings make when everything mechanical in them is running at once, but quieter in the way that late hours are quieter, which is less about sound and more about the removal of expectation. Nothing is about to happen. The body knows this and relaxes accordingly. And somewhere in that relaxation, in the weight of a blanket or the particular pressure of a pillow, there are atoms. There have always been atoms. The ordinary matter of an ordinary night, arranged into the shapes of ordinary things, doing what ordinary matter does when nothing is disturbing it. Holding. The whole conversation that has been happening across these chapters, the Bodmer-Witten conjecture, the 3-flavor stability argument, the Ice-9 logic, the moon's patient testimony, the formal proof that RHIC would not end everything, the anomalous object in Scorpius, the dark matter that might have been there since the first 10 microseconds. All of it was, in one sense, about stability, about what it means for something to be at the bottom, about whether the bottom we have always assumed exists is actually where we are. The answer, 40 years after Witten wrote his conjecture, and more than 50 years after Bodmer wrote the paper that nobody quite read, is still not settled, not ruled out, not confirmed. Sitting in the literature the way the original papers sat, present, technically available, waiting for the measurement or the observation that will finally close the question in one direction or the other. Strange matter may be the true ground state of strongly interacting matter. The energy per baryon may genuinely be lower in the 3-flavor configuration than in anything the periodic table contains. The Pauli pressure argument is clean, the directionality of the effect is not disputed, and the parameter space within which the Bodmer-Witten hypothesis holds has never been fully excluded. Or it may not be. The bag constant may fall outside the range where strange matter is stable. The strange quark mass at the relevant densities may be heavy enough that the energy cost of producing strange quarks outweighs the benefit of the 3rd flavor. The hypothesis may be an elegant near miss, a calculation that comes close to overturning the stability hierarchy, but doesn't quite get there, constrained into irrelevance by the actual values of the parameters the universe chose. The universe knows which. We don't. What we have in the meantime is ordinary matter. This specific ordinary matter, tonight, in this specific room, the atoms in the blanket and the atoms in the walls and the atoms in the body that is lying still and beginning, if the night is doing its work, to drift towards sleep. These atoms have been in their current configuration more or less for the entire age of the universe. Not these specific arrangements. Molecules break and form, cells replace themselves. Matter cycles through stars and planets and living things. But ordinary 2-flavor quark matter, up and down quarks locked into nucleons, has been the dominant form of matter since about 10 microseconds after the Big Bang, 13.8 billion years. In thermodynamic terms, that is a long time to be above the bottom. Not above in a precarious sense, not trembling on an edge, The barrier between ordinary matter and the hypothetical lower state is genuinely high, high enough that spontaneous conversion has not occurred anywhere in the observable universe in all that time, high enough that the physicists who examined the question most carefully concluded that the risk from particle accelerators was negligible, and the cosmic ray evidence was reassuring. The atoms in this room are not about to change. The night is safe in every practical sense, but in a precise thermodynamic sense. And thermodynamics is precise, that is one of the things that makes it trustworthy. There is a difference between stable and at the bottom, between held in place and arrived, between matter that has settled and matter that stopped moving before it got there. The falling, if that is what it is so slow as to be functionally imperceptible. So slow that it isn't in any observable sense happening. The barrier holds. The weak interaction moves too slowly at ordinary densities. The universe's most stable configuration sits just out of reach of everything currently in existence, separated from ordinary matter by a sequence of events whose joint probability approaches but never quite reaches zero. Approaches but never quite reaches. That qualifier has been present throughout, in different forms, in different chapters. The moon argument constrains but does not exclude. The accelerator reviews close the argument tightly, but acknowledge residual uncertainty. The Bodmer-Witten conjecture is unproven in both directions, neither confirmed nor refuted, sitting in the parameter space like a door that has not been tested. The object in Scorpius fits strange star equations better than neutron star ones without being confirmed as a strange star. The dark matter that might be primordial strangelets is consistent with observational constraints without being evidenced by them. Everywhere the same shape, not proven absent, not confirmed present. This is the actual texture of the question, and it seems worth letting it be that rather than smoothing it into something more resolved. Physics has open questions. Some of them are open in the way that a problem is open, known to have an answer, waiting for the right technique to find it. This one feels different. It feels open in the way that some questions about the universe's deep structure feel open, genuinely uncertain at the level of the parameters, dependent on measurements that have been improving for decades without quite closing the gap, theoretically alive in a way that makes it neither dismissible nor confirmable on current evidence. You're made of matter that may not be at the bottom, not in danger, not about to change, but oriented in the precise thermodynamic sense, toward a lower state that the universe has been hiding somewhere in its parameter space for as long as matter has existed. The quarks in your atoms have been in their current arrangement for longer than the Earth has been a planet, and they will remain in it for longer than the Earth will last. The barrier is high enough, the improbability is steep enough, but improbable is not impossible, and the bottom is still the bottom. And somewhere in the interior of objects 10 kilometers across that contain more mass than the Sun, the conditions may already exist where the barrier doesn't apply, where the third floor is open and occupied, and the quarks have found the configuration that ordinary matter, sitting in the low-density universe, has spent 13 billion years being unable to reach. This project is self-funded and independent. No sponsors, no institution behind it, just the work and the people who find value in it. To everyone supporting it on Patreon, thank you. You are what keeps this space going. The night is quiet. The atoms are holding. The question is still open. Somewhere the universe prefers something other than what we are made of. Whether it has gotten there yet, whether it is getting there now in places we cannot see, whether the scaffolding of dark matter that holds galaxies together is made of the same substance that would, under the wrong conditions, consume everything it touched. These are not rhetorical questions, they are real ones. with real answers that the universe is keeping to itself for now. The atoms in the blanket are still falling, in the only sense that matters tonight, slowly, imperceptibly, held in place by a barrier that has never failed, toward a bottom they have never found. Sleep comes for ordinary matter too,